Yeah. So, hi guys, welcome to the video. Now, I'm going to teach you about self-attention in Transformers. This phenomenon focuses on how look. This revolves around how to understand the words better, in the context. So basically, what I'm saying is, if you read this statement of the pizza came out of the oven and it tasted good, what does it refer to here? Does it refer to oven or does it refer to pizza? So this is one of the fundamental kind of things self-attention solves. To better understand it, let's actually take an example scenario. We'll actually take the same example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So let's say the pizza came out of the oven and it tasted good. So the let us say so now this is one example sentence, but let's say our vocabulary size is around 5,000. So we are dealing with data which has 5,000 different words. And one more thing I want to say here, for our convenience, we are taking one word as one token. A token is usually three-fourths of a word. That is how it is described. But for the convenience here, we are taking it as one token. We'll take the sequence length the same as the number of words or number of tokens in this example sentence, which is 2, 3, 4, 5, 6, 7, 8, 9, 10. Sequence length is nothing but the number of words. Batch size here will be taking it as one. Batch size is something. It's just that how many examples you're going to send GPU or to GPU for processing at once. So this is just a toy scenario, like one batch size should be fine. So usually the input dimensions are your batch size, your sequence length, and so there is vocabulary size and also there is uh, dimensions per word. So what does that mean? So let's say you have some word as cat in the dictionary. So that cat usually, like if we have to represent it in the form of numbers in one hot encoding vectors, if we do something like 0 1 0 we say this is three-dimensional. If we represent it in 5 dimensions, then we represent it with five numbers. So here, let's set a vocabulary size which is easy to work with. And I want to go our vocabulary, not vocabulary size, sorry. Let's set an embedding dimension and let's take that as 50. So in our scenario, now each and every word. So let's say we have words like cat, we have words like pizza, dog, bike, etc. All these are represented. All these are represented with 50-dimensional vector, right? So it's fine till here. What next? Now, once you know what kind of dimensions you have, and once you know what kind of like input you are processing, now how do you represent this particular sentence for the model? It would be exactly, I'll come to this later. It would be exactly 1, 10, 50, right? Now this represents our input sentence. We have embedding of all the tokens, right? So we have some 5,000 tokens or words in our vocabulary, and we have embeddings of each and every token. So what is the use of WK, WQ, and WV? What are these? So like basically, if to be honest, if I have to write this as query, not exactly, there is a computation. Sorry, this is key, query, and value. right? What are these? So don't go by the like. There are a lot of definitions out there, which are confusing for some people and which are not. But let me explain you in a like in a generic way what these three does actually. You all know this concept of dot product, right? So imagine like there is vector 1 and there is vector 2. When you do a dot product between these two, let's say if how do you know that these vectors are in the same direction or these vectors are similar when there is a high value? And similarly, like when there is a very low value for this one, we say the vectors are not quite similar and they are in different directions, right? So now you might ask, in order to measure to like let's say actually the previous sentence is too long, so let's just take a simple sentence. The cat sat on the mat, right? Now when you take this sentence, you want to see how each and every word is paying attention to all other words along with itself. Paying attention is nothing but it's a fancy way of saying how might I incorporate information from other words into me. So let's say basically if you represent sat with 5, 1, 2 as a vector, now based like after some performing attention mechanism, you got some information of cat, some information of some information of mat. This slightly changed. The representation for sat slightly changes. It might be 4, 2, and 3.9. Now, why does it change? Earlier, this was only representing sat. Now, this vector is representing the context from these vectors. So, attention is nothing but paying attention is nothing but getting that information from all these vector, like all these different words into the attending word. So, if I say sat attends to cat, sat attends to cat, that means what I mean is SAT is getting some information and some numbers. So if we want to talk purely in numbers, basically SAT is ready to change itself based on what cat is saying. Right. Now this has a much more higher, you know, contextual representation. Right. Okay. Now you can simply say if you can take this as V1 and if you can take say the same sentence as V2, you can just do V1 dot product V2 and then find out attention between all these words, right? So basically what that happens is attention is a square matrix. So there is some slide that I've kept here for you guys. Maybe wait, let me find it. Okay, good. If you see here, oh no, let me delete one. If you can see here, the train left the station on time. Now this is the same one token, okay? Like one, you can say one sentence and multiple tokens. So this is the same sentence. Now attention is nothing but comparing the similarities. So firstly, you can see all the diagonals are one because a word that attends to itself, like it's the most similar. If you consider this is the space, so coordinate axis, if this is and if this is also the dot product between these two is one because like the dot product is cos and cos 0. The angle between these two is 0 and hence the value is 1. But if you look at this station, right? station attends to train, oh, sorry, station attends to train point 8. That means you can see station has some information encoded from train and some information encoded from left, some information because some information is encoded from the, etc. So the station vector is changing based on all these surrounding vectors. Now, uh, yeah, you might as well do v1 times v2. Here v1 and v2 are the same vector and compose this matrix, right? Because it's the same thing. You're obviously right. We can do that. But the problem is here we have already assumed that we have ideal representations for the train, left, maybe station, etc. Right? We already have assumed ideal representations for all of them. We have WQ, WK. Let's talk about these two matrices. WQ, WK, just to represent these tokens in a different space where they can express themselves more. So let's say this particular the vector, when you multiply by weight matrix, this weight matrix does a linear transformation of that vector. This try to represent whatever vector that you have in a rich space where capturing semantic relationships between these tokens becomes easier. So WQ and WK, these weight matrices are optimized to capture semantic relationships. So the same statement, the train left the station on time, gets projected as a Q matrix, no, no, like as a query, and the same statement, the train left the station on time, gets projected as you know K key. So there's the same vector gets projected as query and key. Now you might see people interpreting this as different sorts of things, saying key is looking for what do I have, query is looking for sorry, query is looking for what do you have, key is saying I have this, this, and this. No, this is all fine for interpretation purposes, but actually what is happening is you are just projecting the same input representation, whatever you have, into WQ and like into a different space and then calculating this attention scores. Now, now the problem is actually I can't say this as a problem, but let's go the next step. Next step. So once you have the attention matrix, okay, if you can see here, let me clear a few things out for you. All right. So right now you can see this attention matrix. So what attention matrix says when constructing the word station, constructing the vector for the word station, you don't construct the vector only for station. You take so let's for simplicity assume that this all values sum to one. If they sum to one, what it is saying is consider 20% of the and 80% of train, 60% of left. So whatever vector that left has, consider 60%, some amount of values. Consider 80% of train. All these values will be taken into account while designing for the vector of station, right? But you earlier, I said like I will discuss value vector, like value matrix separately. Now the value matrix comes into picture. The What is the formula for calculating attention? Attention is softmax of K times Q transpose by root D whatever plus V, right? What this says, we did K dot Q transpose, like we projected K and Q like this same, project the input representations by multiplying with their corresponding weight matrices. And then we took a softmax. Root D is nothing but this is just to maintain the training properly, right? This is just to maintain the training properly. Now we multiply this with V. What is V? V is the weight matrix of value times input representation. So earlier I said we project the same input representation to different spaces for keys and queries. The thing is we also project the same input representation as values into the different space. Now be careful. WV, WK, and WQ, they all are different matrices. They all are initialized randomly and they contain different different values and they serve different purposes. So these serve, like I'm telling this for our understanding. WK and WQ, these both matrices are responsible for identifying semantic relationships or how words behave with each other, tokens, how the tokens attend to each other. Basically, these matrices are optimized for computing attention scores. And the value matrix, this is optimized for predicting the next word. Now, what do I mean by that? Or like you can also think it as based on this attention scores, I need to construct a vector. How that vector should look like. So you say consider 20% from the, consider 60% from state train. Now this we say like while like, keep this in mind while constructing the vector for station. These are only percentages, right? Now, in order to convert this to a vector, we need to multiply it with this value. Simple. What is this value? This is an enriched input representation. Now, what do you get? I said this is always the square matrix, right? So, attention is a square matrix. So, if you have 10 tokens, the attention matrix would be 10 by 10, right? If you multiply that with the value matrix, which is of, let's say the value matrix operates on full space, which is of 50 dimensions, you will get 10 by 50. And what is this? And so on, like till 10. You have 10 tokens, and each token has its corresponding representation, representing vector, which is of 50 dimensions. But the only difference is now this vector has much more context, and this is how the things work. Yeah, thank you for watching the video.